Weber from Max Planck Institute, Germany, MPE. I know Mickey when he was a PhD student at the University of Arizona. I was there. And then he's now a postdoc at Max Planck. And today he's going to talk about modeling neutron star pulse profiles.
Okay, thanks. Here's just a quick outline of what I'm planning to talk about. Pretty quick introduction of why we should care about neutron stars in general and pulse profiles modeling in particular. And then I'll walk you through how we model pulse profiles. And in particular, what I'm mostly interested in is all of the relativistic, both special and general relativistic effects that we have to take into account in order to get accurate models. I'll talk about the parameter space of the models and compared to the observables of what we can actually measure from the pulse profiles. And then I'll spend a little time talking about the beaming of the radiation from the surface of the star. And then some additional uncertainties that we haven't worked out yet. That's the to-do section for what we still need to do. So starting off, neutron stars, why should we care about them? Neutron stars are some of the most extreme objects that we can observe in the universe. They have extremely high densities, up to 10 times the nuclear saturation density. We observe them spinning at up to 716 times per second, which translates to a surface velocity of 0.2 or 0.3 the speed of light. So the surfaces are moving extremely quickly, making special relativity a necessary component in our analysis. They're very compact, so this GM over RC squared is a measure of how compact the neutron star is, and where a black hole has a compactness of 1, and you can see neutron stars already have a large compactness. And then this little comic of how dense is the matter inside of a neutron star. If you took a sugar cube, like 1 cubic centimeter roughly of neutron star matter, that has as much mass as all of humanity on Earth. All right, so really, these are extreme and very dense objects. In fact, they're so dense that we don't really understand how matter behaves at those pressures and densities. And the way we quantify our lack of understanding is through this equation of state, which relates the pressure and density of the matter inside the neutron star. And it turns out that there's a one-to-one relation between this function between the pressure and density and the function between the mass and radius of a neutron star. So if we observe lots of neutron stars that might have different masses, we expect them to also have different radii. And the relation between the mass and radius is just determined by the equation of state of the matter in the interior. We have some idea of the equation of state. We can measure it in laboratories on Earth up to about nuclear saturation density. That's if we look at large atoms, the nuclei of large atoms, then those already give us some idea of what the equation of state of matter in there is. But like I just said, neutron stars are much denser, so have up to 10 times nuclear saturation density, and we can sort of extrapolate of what we think might happen at those densities, but we're not really sure. And the uncertainty here is so these are several different models proposed by people who have done this extrapolation and modeling in a different way. And you get widely different mass and radius measurements. They predict different maximum masses for neutron stars, and you can get radii from maybe 7 kilometers all the way up to 15 kilometers, depending on what parameters you use in your models. So there's several ways that people, in trying to measure this equation of state, usually the best way I think that we have of measuring the equation of state is trying to measure masses and radii of several different neutron stars. Ideally, we would measure several different masses, measure the radii precisely, and then we could compare it to these model predictions and determine which one is the correct equation of state. And I think one of the most promising, for sure, methods for measuring the mass and radii is by observing pulse profiles from neutron star surfaces. So these arise, these are X-ray pulse profiles. So these arise from some sort of temperature hotspot, so a temperature variation on the surface of a neutron star. There's a variety of ways those can arise, either from accretion. If the accretion is funneled by the magnetic field onto the magnetic poles, then those magnetic poles are hotter than the rest of the surface of the neutron star. Or from magnetic return currents. We'll talk more about those later. But the magnetic field of neutron stars is strong enough that it lifts some of the material off of the surface, and then it funnels it back onto those same magnetic poles, and the particles, as they bombard the surface of the neutron star, heat up those magnetic poles, and again you get these hot spots. Or even in X-ray bursters, that's when the whole surface of the neutron star explodes in a thermonuclear explosion. Sometimes the explosion starts in one place and then spreads out over the whole surface, and the neutron star is spinning fast enough that it spins many times during this spreading of the burst over the whole surface. So when we watch the burst during the rise, we see these oscillations as the burning part of the surface comes into and out of view. So whatever the mechanism of how these hotspots arise, the hotspots produce pulse profiles, because as the neutron star spins, in general, the hotspots aren't exactly on the poles of the star, on the rotational poles. And so if they're offset, then as the hotspots come into and out of view of the observer, we see a modulation in the brightness of the neutron star. It looks like this. This is this is a model. I'll talk a little bit about how we generate these models, but in the simplest sense, you have a hotspot, you have it going around. Really, the neutron star should be spinning, but my animation isn't that fancy. And as it comes into view, you see this rise, and then as it goes out of view again, you see the brightness decrease. And the shape of this hotspot, of this pulse profile, encodes information about both the mass and the radius, which we can hopefully, so the idea is you measure these pulse profiles very precisely. If you measure them precisely enough and do the modeling correctly, then you should be able to calculate the mass and radius from just the shape of the pulse profile. Okay, so how do we model pulse profiles? We've already talked about neutron stars are highly relativistic environments. Speed's 30% of the speed of light, compactness up to 0.3. Spin parameter, that is the dimensionless angular momentum, up to about 0.1, which means that we need to consider both special and general relativistic effects on the emission from the surface. So special relativity has two effects, we can say. The Doppler shift changes the frequency of the light. When the spot is moving towards you, it looks bluer, and when it's moving away from you, it looks redder. And then the second order effect, there's this boosting as well, that the spot looks brighter when it's moving towards you and fainter when it's moving away from you, which leads to a steepening of the pulse profile. It goes from being just a perfect sinusoid, it shifts it a little, it steepens the rise because it looks brighter, and then it changes the shape of the pulse profile. Then moving on to gravity, general relativity. These stars are massive enough and have a strong enough gravity that lensing becomes important. So light passing near the surface of the neutron star gets bent. These are just trajectories of photons coming from infinity, and you can see they don't travel in straight lines. They get bent onto the surface. In this case, I've done the simulation modeling the photons coming from infinity to the surface, but it's the exact same trajectory if it goes backwards from the surface out to infinity. So the upshot is you could see, for example, if we look at this photon trajectory right here, this photon will reach your eyes standing at infinity, even though it's behind the neutron star. If this were a classical Newtonian sphere, we wouldn't be able to see that part of the neutron star. So gravity makes it that we can see more of the neutron star than we would otherwise be able to. So this animation just shows what happens as this is a neutron star of a certain radius, I think it's 10 kilometers. And what I'm doing is just turning up the mass, so increasing the amount of gravitational lensing up and down, actually. You can see when the mass is small, the surface looks bluer, and the whole star looks smaller. And then as the mass gets turned up, we can see behind the neutron star and more. The whole surface gets redder from the gravitational redshift, and the apparent size of the star looks bigger. Okay? So this is what would happen just in Schwarzschild gravity. This neutron star is not spinning, it's a perfect sphere, and that makes it very easy to model. We can write down everything analytically, and everybody would be happy if that were all we have to consider. But neutron stars, yeah?
What's the mass range you were considering for that?
What's the mass? I don't remember what I used for this particular simulation. It's a pretty extreme range just to make it more obvious. I think it goes from like 0.5 to 2 or something. So the problem is neutron stars are not just perfect static spheres that are not spinning. As we already said, they are spinning up to 700 times per second, which has several effects on both the star itself and the space-time around the star. To first order in spin, we need to consider frame dragging. That is when the space-time around the star is dragged along with the rotation of the star. And then to second order, the star is no longer spherical. The surface becomes oblate. It starts looking more like this picture over here. So the poles get squished in and the equator spins out a little bit. And then this oblateness causes there to be higher order mass multipole moments. So the mass of the neutron star is no longer spherically distributed around the center. We can't just consider it as a point mass. We have to consider all these, how the extra mass changes the bending of the light. Here's just a couple different regimes in which we could do our modeling. In the simplest case, like I said, everything would be very simple if neutron, we wouldn't see any pulse profiles, but other than that, everything would be very simple if neutron stars were not spinning at all, because then they would be perfectly spherical, the space-time would be Schwarzschild, there would only be one parameter, which is m over r, and we can use this approximation for our modeling as long as the neutron star is spinning at less than about 100 hertz. Faster than that, we need to start considering first-order effects of the spin, namely the frame dragging. And the appropriate metric for that is the Kerr metric, which now has 3 parameters, mass, radius, and the moment of inertia. And that's a good approximation up to about 500 hertz. For the most rapidly spinning stars, we need to consider also this changing of shape of the surface and the extra mass moments. And there's a metric called the Hartle-Thorne metric, which is an analytic approximation of the space-time up to second order in spin frequency that has some more parameters, but lets us go up to about 800 hertz. And then after that, if we ever find a neutron star spinning at 1,000 hertz, even this approximation won't be good enough, and we'll have to do a numerical model of the space-time, numerically model the neutron star shape, consider all of the higher mass multipole moments. Problem with this is that it'll depend on the equation of state, which is what we're trying to measure. And so you're left in this kind of circular loop of you need to assume an equation of state to interpret your measurement that you're trying to make of the equation of state. So we're trying to do everything in this Hartle-Thorne metric is Okay, so we use this Hartle-Thorne metric. We have a code that does the ray tracing, so it calculates all of the photon trajectories from infinity to the surface of the star, taking into account the oblateness, the quadrupole moment, the frame dragging, all of the Doppler shifts on the surface, and that gives us these models. It gives us a time series of images of the hotspot on the neutron star surface, which we can then use either to make these animations, or we can just integrate over the whole hotspot, calculate the total flux, and we get a light curve of the pulse profile of the star. Okay, so if we can make a model of the pulse profile, what's the parameter space and what can we actually observe? What can we hope to observe of the pulse profiles? So in principle, the parameter space is large. We need the mass of the neutron star, the radius of the neutron star, we need the moment of inertia, we need the quadrupole moment, all of these, we need the oblateness of the star. All of these 5 parameters are determined by, so they're all related to each other by the equation of state. So if you know the equation of state of the neutron star, then for, say, a particular mass, you could calculate the radius, the moment of inertia, the quadrupole moment, and the oblateness of the star. But like I said, the equation of state is what we're trying to measure, and so we don't really want to have to make an assumption of the equation of state. And then aside from those, there's some geometrical parameters, like the inclination, how inclined is the neutron star with respect to us, how big is the hotspot that is causing the pulse profiles, and where on the surface of the star is the hotspot located, is another parameter. So there's a lot of parameters that go into our models, and really, we're probably only going to get about 4 observables. So the first observable is just the amplitude of the pulse profile, the fundamental amplitude. We can measure the amplitude of the first harmonic, so how different is our pulse profile from a sinusoid, just to have Fourier decomposition. And then we can observe the pulse profile in several different energy ranges and ask how does the color change? So what is the color amplitude of the pulse profile? And the last observable we have is we can ask what is the difference in phase between the color pulse profile and the flux profile. So does the star look bluest when it's also brightest, or is there some shift in phase between those two? So looking at this, it doesn't look good. We have we have 8 parameters that we're trying to all fit with only 4 observables, which seems like a hopeless task. But luckily, there's it turns out that there are several universal relations between different parameters that we can use to help us out. So these are the so-called I love Q relations. And it turns out that for a broad range of equations of state, you can calculate, say, the moment of inertia and the quadrupole moment, knowing only the mass and radius of the neutron star. So if you know the mass and you know the radius, then no matter what exactly is happening in the interior, what exactly the equation of state is doing, they all predict more or less the same moment of inertia and quadrupole moment. And then using those in the Hartle-Thorne metric, if you know the moment of inertia and the quadrupole moment, it turns out you can analytically derive exactly what the oblateness of the surface is. So we can relate those parameters, which all depend on the equation of state. We can get rid of the equation of state dependence and just say if we have a mass and a radius, which is what we're trying to measure, then we can assume we know what the moment of inertia, the quadrupole moment, and the oblateness are doing. So that reduces us down to 5 parameters on this side with 4 observables, which is a little better, but still more parameters than observables. So I'm going to argue that the spot size is the easiest of those parameters to get rid of. It turns out the spot size and the stellar radius have a degenerate effect on the pulse profile. So these are two different sets of models. On this side, I'm increasing the radius from 9 kilometers to 10 kilometers to 11 kilometers for these pulse profiles. And then for the same inclination and location of the spot, I'm increasing the size of the spot from 2 degrees to 10 degrees to 25 degrees to 50 degrees. And you can see in both cases, the change is mostly in the fundamental of the, so making the spot bigger decreases the amplitude of the pulse profile, and making the neutron star smaller also decreases the fundamental amplitude. So we can ask the question, how big does the spot have to get before it starts really influencing the pulse profile? So if we just want to say, we're just going to assume our spot is small, and we get rid of the radius and just say it's an infinitesimal spot, how big does it have to be before that causes a problem and gives us a wrong radius measurement, so to speak? So you can see here, just from looking at this estimate, there's 5, 10, 15, and 40 degree spots corresponding to the 4 animations on the slides. And you can see 5, 10, and 15 all look more or less the same. 40 degrees, you're really changing the pulse profile by a lot. The fundamentals, so the amplitude depends relatively weakly on the spot size, like we said. So this is just the amplitude of the fundamental, or these contours, as a function of the spot radius and the spot inclination. And you can see, as long as we're not exactly edge on, then things don't change much up to 40, 50 degrees maybe. The higher harmonics are affected a little more strongly. So this is the second harmonic of the pulse profile. And it turns out the radius measurement that you get from the pulse profile depends most strongly on C2 over C1. So this is C2 over C1 as a function of the angular radius. So we can ask, if we make the assumption that the spot is small, and then we use that assumption to model a spot that is not small, how much of an error do we make? Or how big can we make our spot before we get a 10% error in the radius? Let's say we want to measure the radius to 10%. How big can we make the spot before our infinitesimal spot model is no longer a good approximation? So this shows the maximum spot size that you can have, these contours, that give you still a less than 10% error in the radius measurement as a function of the location of the spot, the colatitude, and the inclination of the observer. And I've shaded out 2 regions here. In this bottom region, you are looking at the pole of the neutron star, or the spot is so close to the pole of the neutron star that you don't really see any modulation in the light curve, or the modulation is so small that we don't have any hope of measuring the second harmonic anyway. All right. So if this is the case, then we can't measure the second harmonic well enough to determine a radius anyway. And in this region up here, the hotspot at some point, as it's going around the neutron star, is actually hidden from the observer entirely. And so we get an eclipse. In that case, we no longer care so much about the harmonics. We have to do a fitting of the pulse profile that includes this eclipsed part, so here's just some light curves. This is a parameter configuration where the spot is very near the equator, and we're looking at the neutron star almost edge on, or I think we're looking exactly edge on, and the spot is 10 degrees off of the equator. And you can see for a small spot, there's this region of the light curve where the flux drops to 0. That is, the spot is entirely hidden behind the neutron star. As we make the spot bigger, though, the time of this eclipse decreases, and if we make it big enough, then the spot is covering so large a fraction of the surface that it actually never gets eclipsed entirely, and we get this light curve that doesn't show an eclipse anymore. So for these cases, we can ask again, how big can we make our spot, or how much does the eclipse duration change depending, so this is how big can we make the spot without changing the eclipse duration too much, because the eclipse duration will then tell us something about the radius of the star. And again, it looks like around 15 degrees is a good estimate of how big we can make the spot without significantly affecting our mass and radius measurements. So the question is that reasonable? Like, can we expect smaller than 15-degree spots? So these are some statistics of the sources that NICER is looking at. NICER is a satellite that was launched a year and a half ago. It's bolted to the space station, it's an X-ray mission, and it's just staring, a key component of the mission is just staring at several of these rotation-powered pulsars, measuring the pulse profiles, and deriving a mass and radius measurement. So on the left we have the rotation-powered pulsars, on the right we have accretion-powered pulsars, and I'm going to focus mostly on these rotation-powered pulsars, and you can see that for most of the sources, if we do a hand-wavy calculation of how big we expect the spot size to be, just based on the spin frequency and what we know about the magnetic field, we see that most of them have spot sizes that are smaller than 15 or 20 degrees. So I'm going to use that as an argument that we can take out the spot size, just say the spot size is small, and then we're left with our 4 parameters that we're trying to measure, and 4 observables that we have to do it with. So now some of you might be thinking, wait, what do we know about the beaming of the radiation? Shouldn't that affect the pulse profile as well? Yes. So beaming is the angular dependence of the radiation emitted from the surface. So does the radiation look brighter if you're looking straight down at the surface, or does it look brighter when you're looking more tangent to the surface? So for example, on our own sun, we have this limb darkening effect, where if you look straight down at the sun, it looks brighter than if you're looking kind of tangent to the surface. That's because the sun gets hotter the further in you go. So here you're looking more at the cool outer layers of the sun, and here you're looking deeper into the interior where it's hotter. Whereas in some cases, like in this planetary nebula, you get this limb brightening, where it's a thin shell, and so you see a brighter emission when you're looking kind of tangent to the surface, because there's just more material there that you're looking through. Whereas if you're looking straight down, you're only looking at this thin shell kind of perpendicular, and so you see less emission. So the question is, which regime do the neutron stars fall under? So to answer that, we need to think a minute about how the hotspots are generated. The hotspots are generated by these magnetic return currents. The material is stripped away from the surface of the neutron star, and so there's these ions, there's these electrons and positrons that are floating around out here, and they get funneled by the magnetic field lines onto the surface of the star. And when they hit the surface of the star, they heat the atmosphere of the neutron star, and that heating causes the hotspots that we observe. So there's 2 different methods, there's 2 different mechanisms by which these electrons and positrons heat the atmosphere. The first is by binary collisions, just the electrons or positrons coming in directly hit the electrons or positrons in the plasma of the atmosphere, transferring their energy to the atmosphere and causing it to heat up. And the second effect is the collective effect, or the plasma waves, Langmuir waves, which is the electron, in this example, it's an electron passing through the plasma, causes a wake behind it of electrically positively charged material, and that causes all of the electrons to be pulled back into that wake, and it sets up this oscillation at the plasma frequency. And that oscillation drags this electron backwards. It causes a drag on this, which transfers energy from the electron also into the plasma. Now, which of these effects is the dominant source of energy transfer depends on where in the atmosphere you are. If you are at small optical depths, then the binary collisions dominate, and at large optical depths, these collective effects dominate. So this is the electron wavelength divided by the Debye wavelength of the plasma, which is a measure for which of these, whether the electrons in the return current are going to see the plasma as individual electrons to interact with, or whether they're going to see a sea of charges that they're going to more have a collective interaction with. So knowing these two effects, we can ask, where does the energy get deposited in the atmosphere? So here, this is a toy model of just a gray atmosphere that you throw electrons and positrons at. For right now, these are just constant energies of electrons and positrons in the return current, characterized by this relativistic factor, so gamma of 2 up to gamma of 500. And as you might sort of expect, the more energetic the electrons are that you throw onto the atmosphere, the deeper they penetrate before they deposit their energy. You'll also notice most of the energy is deposited in this very small area. This is the stopping depth of the plasma, which is just because the energy transfer becomes more efficient the more you slow down the electrons. And so you get this kind of building up effect where the more energy the electrons have lost, the quicker they lose their energy, and so then they stop pretty much in a very small range. So then if we know these depths, we can ask what sort of temperatures do we see in the atmosphere as a result. So this thick gray line is the